In this video, we're going to discuss more equations and applications of your logarithmic and more specifically your exponential functions in regards to applications. Now that we know all of our properties or our rules of logarithms, it opens us up to being able to solve more and more equations. And so we already reviewed how we solve exponential equations by getting a common base on both sides of the equation. Well, now that we have logarithms, one method of being able to solve these exponential equations is to rewrite the equation as a logarithmic equation, like converting from logarithmic notation, exponential notation to logarithmic notation. Or we're going to do something called take the natural log of both sides and use the power rule, because in exponential equations, our variable is in the exponent and we need a way to allow us to get that variable from being in the exponent so that we can solve. And so one way to do that is to use the power rule from logarithms, and we'll see an example of that there in these examples here. And then we just solve the resulting equation. And so let's look at these examples here. In part A, I have 3 to the 3x equals 84. There are actually two methods or two ways that we can do this. I'm going to do this one using this first method up here, which says to rewrite as a logarithmic equation. Remember, when our base is raised to an exponent and that equals some value, we could rewrite that as a logarithmic equation as saying log at base 3 of whatever our exponential equation equals, which is that 84, or that expression equals our exponent on our logarithm, right? And so I converted that to a logarithmic equation, and now it's actually a linear equation because this is x to the first power, and that's just a constant. This is an irrational number. And so I can divide both sides by 3, and I'll have this equation completely solved, right? So x equals the log at base 3 of 84 divided by 3. Now, sometimes people don't like to use this method here for the simple fact that some calculators don't have the ability to do log at different bases other than the common logarithm and the natural logarithm. And so an alternative method for solving this equation here would be to take the natural log of both sides, right, which is the second method over here. And so when we take the natural log, you got to make sure that you're taking the natural log of positive numbers, right? And so since 3 to the 3x is always going to be a positive value, I can take the natural log of that side. And I'm specifically choosing the natural log because that's one of the things on my calculator. You can also do the common log. But when I do that, I could use the power rule, which allows me to bring that 3x out front and reduce that to a 3x times the natural log of 3 equals the natural log of 84. And when I see this written this way, notice this is 3 times x times natural log of 3. Again, the natural log of 3 is an irrational number, so I have two numbers multiplied by x. Well, to undo the multiplication by constants, we divide by those constants. So I can divide both sides by 3 ln of 3, and they cancel on this side, and I'm left with an x here. And then I have natural log of 84 over 3 natural log of 3. And that is my solution. Both of these, if you put them in a calculator or a computer, they're going to give you the exact same decimal approximation. Let's go to part B. Now, you don't have to use both of these methods. I'm just showing that both of these methods work on this example. In example B, since we have exponential expressions on each side of this equation, what I'm going to do is I'm going to take the natural log of both sides. I'm not going to rewrite this as a logarithmic equation, which is here, or in logarithmic form like I did in the first method for part A. I'm going to do it like this second method that I did for part A. So since e to the x will always be positive and 2 to the x plus 1 is always going to be positive, I have that the natural log of e to the x equals the natural log of 2 to the x plus 1. The natural log and e, they cancel, and so I'm left with an x. And here by our power rule, we can bring this out front, right? So that would be an x plus 1. Notice I'm putting this into parentheses because both of those things in that sum have to be multiplied by the natural log of 2. Now, the natural log of 2 is a number. So I can use my distributive property because I have a linear equation. I don't want my x's on one side by itself. Right now, it's on both sides. So I'm going to have the natural log of 2 times x plus the natural log of 2. Well, I'm going to subtract the natural log of 2 times x from both sides so that my x's can be on one single side of my equation and my constant terms are on the other. And then notice here, both of these terms have an x in them. And so I want to simplify, so I'm going to factor out the x. Sorry. My computer is being a little slow, so I do apologize. I hope that the sound is working just fine. but I can factor out an x out of both of these terms. And remember, this is just a number, right? So if I have x times a number, I can divide both sides by that number to isolate my x. And I can see right here that it cancels on my left-hand side, and so I'm going to get x equals that natural log of 2 over 1 minus the natural log of 2. And so that will be the solution to my equation here. Notice here, I didn't check my solutions here. These are exponential equations. For exponential equations, your domain is all real numbers. And so when I get a solution and I feel like my work is all the way correct, then I'm going to be fine with that solution. Now, when I start to solve logarithmic equations, which is what we're going to do in this next example, or these next examples, I'm going to want to always check my solutions, because with logarithmic equations, our domain is no longer all real numbers. So we always have to check our solutions. And so let's look at some guidelines that we can follow to solve logarithmic equations. One of the things that we want to do is we want to condense the logarithms that have the same base on each side of our equation. Just condense it all the way down. Sometimes they're written in expanded form, get it in condensed form. And then there's two methods that we can use to solve these logarithmic equations. We can either change it to exponential form to have an exponential equation, or we can use the one-to-one property. Remember, logarithms are one-to-one functions. And so almost like the exponential, remember when we first started talking about solving exponential equations, we said that, oh, if we have exponential functions that are written in this form, and I have a to the x of 1 equals a to the x of 2, then if this equation is true, then it means that those exponents have to be equal, because an exponential function is one-to-one. Well, the same thing happens with logarithmic functions. And so if I have log at base a of x1 equals log at base a of x2, then by the one-to-one property, if this equation is going to be true, then the arguments or the inputs of my logarithmic function have to be equal to each other. So this is another method by using the one-to-one property. This is another method that we can use to solve our exponential equation, our logarithmic equations. Let's look at an example, or two examples. And then once we use either this or that method, we solve the resulting equation, and then we're going to check our solutions like I said before. And so I have log at base 3 of x minus 1 minus the log at base 3 of 2x equals 4. Now notice here I have logarithms that I have the same base. I'm going to write it as one single logarithm. And when there's a subtraction, we can use that quotient rule for logarithms. And I get a logarithmic equation that looks like this. Now, for me to solve this equation, I'm going to have to rely on changing this or converting it to exponential equation, right? I can take my base and raise it to the exponent, which is 3 to the 4th, and it should equal what I'm taking my logarithm of, right? So I have x minus 6 over 2x equals 3 to the 4th power. Now, 3 to the 4th power, went up too far, is 81. So I get x minus 6 over 2x equals 81. What I can do is I can try my best to solve this equation for x. This is a rational equation now, so it's not linear, it's rational. I can't have my x in the denominator, so I can multiply both sides by the LCD or cross multiply. It's going to give you the same result. So I multiply this side by 2x, and I'm going to multiply this side by 2x. And when I do that, the two x's are going to cancel on my left-hand side. I get x minus 6 equals 162x. If I subtract x from both sides, I'm going to get 161x, and then divide both sides by 161, and I get x equals negative 161. I have to check my solution. So I'm going to go into my original equation, plug in this value for x. All right, if I plug in this value for x here, I'm going to get a negative number. I'm not worried about exactly what negative number it is, but I'm going to get a negative number, right? Because negative 6 over 161 minus 6 is negative. And I can't take the logarithm of a negative number. And so since that would make this expression undefined, in fact, it would also make this expression undefined, I know that this is not my solution. And since that was my only possible solution, I know that this equation has no solution. So the solution set is the empty set. So remember to go back and check in your solutions. Just make sure, if you're confident in this work, you're confident that you didn't make any mistakes in this work, make sure that you go back in and make sure that you're Your possible solution is in the domain of each of these functions that make up your equation. Let's go to part B. I have the natural log of x plus the natural log of x plus 2 equals the natural log of 8. Again, I'm going to condense this into another logarithmic. It's going to be an x times x plus 2, another logarithm. Sometimes the things I say. All right, so because that is a plus sign, we can use our product rule. And now that I have this, all right, so this is the one-to-one property, right? I have the natural log of something equals the natural log of something. By that one-to-one property, if this is going to be a true equation, the only way for it to work out to be perfect or absolutely true is for the input of that left-hand side equal the input of that right-hand side. This is also equivalent to applying the exponential function to both sides, right? Because if I did e to this exponent and e to that exponent, the e and the natural logs would cancel. All right, that's the one another way that you can think about doing this. But in either case, this is now a quadratic equation because when I distribute and I subtract 8 from both sides, I get x squared plus 2x minus 8 equals 0. I can solve this by factoring, which is nice. X plus 4 times x minus 2 equals 0. And my two solutions are going to be x equals negative 4 and x equals a positive 2. Be sure to check your solution. I can already tell that this one is not going to be a solution because when I try to plug in negative 4 into this or even into that, I'm going to get a negative input, and your natural log function is not defined for negative numbers. However, when I go here, I get the natural log of 2 plus the natural log of 4, and 2 times 4 is 8, so this one works. So my only solution here is x equals 2. So that is my solution set. So we know how to get the x from being inside or the input of our logarithmic expressions, right? You're either going to change it to an exponential equation like we did in this example here, or you can use that one-to-one property to get your x's from being the input inside of your logarithmic functions like we did in this equation here. We're going to review some exponential growth and decay, right? Exponential growth and decay is used to model quantities that change naturally. For instance, when natural, like wood decays naturally over time and continuously, right? And so since that is the case, then we have this model, A equals A sub 0 times e to the RT, where a sub 0 or a naught is your initial amount, our initial quantity. The R is your growth or decay rate, right? If it's growth, it's going to be positive. If it's decay, the R is going to be negative. And T is your time, right? This is very similar from when we were dealing with the economic type stuff, where we say P equals P naught times E to the RT. This is what, and that one was used when we knew that interest was compounded continuously. All right, things change in nature continuously, so we're going to use this formula. So this formula is basically the same as this. Instead of using P for principal and all that stuff like that, and I think we actually use A here for the amount at time T, but we use P naught or P for principal. Here we're using A for the initial amount, A naught for the initial amount. And so let's use this example here. It says, how long does it take for 2.4 grams of carbon-14 to be reduced to 1.3 grams of carbon-14 by radioactive decay if it decays at a rate of 15% per year, right? And so since I know that this is something natural, then I'm automatically going to use my formula. If you want to use the formula PE to the RT, by all means do so. You don't have to remember that this is A naught instead, right? As long as you use the right thing, right? But I'm starting with 2.4 grams. It decays at a rate of 15%. So that's a negative 0.15. I don't know how long it takes to decay, but that's what I'm trying to figure out, how long it takes for it to end up being just 1.3 grams. And so I have an equation. The variable I want to solve for is t. So let's go ahead and divide both sides by 2.4 to isolate this exponential equation, right? So I'm going to leave this in exact form. And so here I have my equation, right? Now there's a couple ways that we can solve this equation, right? This is an exponential equation. Remember, we said we could rewrite it as a logarithmic equation, or we can take the natural log of both sides. What I normally do, and this is my preference, you do not have to always follow my preference, So I take the natural log of both sides. All right. And it's nice when we have this continuous decay and when we use our PERT formula, because when we take the natural log of both sides, that natural log and that e are going to cancel, right? And so I'm going to have the natural log of 1.3 over 2.4 equaling negative 0.15t. Divide both sides by negative 0.15, and we'll have that t is that value, right? And then we can put this value into our calculator. So I want to show you how we can put the natural log in our calculator, since I don't know if we've done that before. And I think this is why my computer's been slow. All right, so I have the natural log of 1.3, divided by 2.4. I'm going to close that parenthesis and I'm going to divide that by a negative 0.15. Press enter and I get approximately, I'm going to round that to 3 decimal places. And because I forget things really quickly and I actually can't see this when it's on my screen, I am going to take a picture of my calculator screen right quick and place it here for me to see. All right, and so I have that this is going to be approximately, I'm going to do it 4 decimal places, 4.0874. And my units is time. Now, when we were dealing with the economic with interest, compound interest, we always did things in terms of years. These problems are going to be in the time frame given in the problem. Now, this one is 15% per year. It is continuously still though. And so I'm going to say 4.0874 years. All right, so that is my solution. The last concept that we want to deal with is what we call half-life. Half-life, and let me allow you to see this. Half-life is the amount of time it takes for a quantity to reduce to half of its original size, all right? And so if I start with 50 of something, the half-life, if I know the half-life is 10 years, then in 10 years, I should end up with 25. That's half of that. And 25 is your half-life. Right? All right. So half-life is a time. It's a time frame. It's the amount of time. All right. Not only can we solve problems about half-life, but we can solve problems about doubling time, or the amount of time it takes something to double if it grows. Or we can say third life, 1/3 life. We don't usually call it that. We'll say how long does it take something to reduce to 1/3 of its size, or 2/3 of its size, or 1/4 of its size. All right. So I can use different factors like 1/2 for half-life, or 1/3 for a third, decay into a third of its size. I can use word like doubling or tripling or quadrupling, and the same concepts would apply. All right. The amount of time it takes it to go to that factor, or reduce to that factor, or grow to by that factor is called that type of time. All right. And sometimes we know the half-life of things, which allows us to get the rate or do other calculations. And so let's look at this example from the medical field. It says the half-life of aspirin in the blood is 6 hours. Suppose a patient receives 81 milligrams of the drug at 8 a.m. How much aspirin is in the blood at 9 a.m.? All right. And so in this example, they give us the half-life, right? That's T equals 6 hours. That is my half-life, right? But what we want to do is we want to suppose a patient receives 81 grams, right? And we want to know how much aspirin is in the blood, the amount in the blood at 9 a.m. But that's 1 hour later, right? Now, if I were just to give you this second part here, in all of these problems, we're going to assume we have continuous decay, okay? We want to know how much is in the blood. So I want to know this variable A here. If they took 81 grams, and I want to know it for 1 hour later. 1 hour is my time, T is 1 in hours. In order for me to figure this out, I first need to know the rate, all right? I need to know the rate at which it's decaying. Since I don't know that, I've got to rely on using my half-life to help me figure that out, right? And so half-life again, all right, this is my formula for decay, exponential decay. And basically what half-life is telling me is that if I plug in 6 for t, all right, I should end up with half of what I started with. Now, this question right here tells me that I start with 81, right? So you could put an 81 here, all right? I'm not, all right? And I'm going to tell you why. Because it doesn't matter what the initial quantity is. If the half-life is 6 hours, I know that I'm going to end up with half of what I started with. So I'll replace my outcome with half of whatever I started with. That 81 is not going to matter. Now, if you wanted to put 81 here and then put 40.5 here, you can, but I'm going to tell you, we're going to try to solve for our rate, which will allow us to solve this problem here. When I divide both sides by a0, I'm going to get that 1/2 anyway. So I get 1/2 equals e to the 6r. And so that 81 or 40.5, all that stuff is going to reduce when I isolate the exponential expression to a 1/2 anyway, all right? So you can choose. I'm just using the a0 here. All right, if I want to solve this equation, my variable is in my exponent. To get the variable outside of the exponent, we have to take the natural log of both sides, or we could change it to an exponential equation. I told you that my preference was to do this. Take the natural log of both sides. And my computer is being very slow. I'm sorry about these changing colors. All right, we're going to divide both sides by 6. And I'm going to get r equals the natural log of 1/2 divided by 6. And so now you can put this in your calculator, but I do want you to know something about some of these exponential equations here. If I put this in my calculator and I use a rounded value, okay, sometimes my answer may be way off, even if I round it to 3 decimal places. 1 decimal place or 3 decimal places versus 5 decimal places can end up with a very different number. Because remember, your exponential function, at a certain point, it grows really quickly. All right, so I can move 1.1 unit over on my x-axis, and my y-axis may go up 100 units because I have exponential functions. And so what I like to tell my students is that when we're dealing with exponential equations, especially application problems, what we're not going to do is round, all right? What I'm going to do to solve this problem is I'm going to put that natural log of 1/2 over 6 in its place. So for me to solve this equation, the amount at 9 o'clock is going to be basically the natural log of 1/2 over 6 times 1, right? And that's the same thing as just natural log of 1/2 over 6. And so let's get our calculator and place this in our calculator. And so I have 81, and I'm going to times e, so second ln. And for those of you who have a calculator that doesn't put your exponent in there like that, make sure you open with a parenthesis, and because you're going to put that division. So I'm going to have the natural log. It opens that. I'm just going to put 0.5. 0.5 and a half are exactly the same thing. Divided by 6. And if I needed to put times 1, I will put that in a calculator like that. I don't need that parenthesis. And I will press enter, and I get 72.1628. All right. Now, let me put that natural log of 0.5. It may not matter in this example because we're at divided by 6. All right, so that's a negative 0.112, right? Let me see. I just want to see if I were to place, if I rounded at 2 decimal places, the natural log of 0.5 divided by 6, if I rounded at 2 decimal places, how far would my result be from the 72 point something? All right, it's not that far off, right? Now it's like it's not even a whole unit apart, but if I go in my math lab or whatever homework system we're using, then that answer may be marked incorrect versus this answer. Now you could use the answer feature of your calculator. So if I, for instance, place that into my calculator, then when I call up the answer feature of my calculator, which is second negative sign, then it's going to actually replace this exact value in here, right? And so if I did 81 times second e to the second answer times 1, when you don't need that times 1 there, then it's going to use the exact value and we'll get that 72.1628. 1628 in there. All right. And so let's put our answer on our paper. It's approximately 72 point, I already forgot, 1628. Remember, this is the amount of the drug at 9 a.m. And so since we started with 81 milligrams, the units here would be milligrams. All right. And so this concludes this video, and I'll see you during our next video.